let's take a look at a little bit more detail here in terms of position vectors. Now, consider in 3D, working in 3 space, the vector A, which goes from the origin to the point P. So I have some point up here, P. And I say P has coordinates A1, A2, A3. So this is my vector A. Now, so A is a position vector of the point P. Any other representation of OP, let's say AB, so down here someplace, I'm going to take point A, which is going to have coordinates, let's call it x1, y1, z1. And over here, let's say this is point B, where B has coordinates, let's call it x2, y2, z2. So here I have vector AB. So any other representation of OP, such as AB, must have coordinates for the points. This coordinates x1, y1, z1, and x2, y2, z2. These coordinates must satisfy and the reason it must satisfy is because AB is a representation of OP. It must satisfy the following. x1 plus a1 is going to be x2. y1 plus a2 is going to be y2. And z1 plus a3 is going to be z2. Now, this all implies, by simple algebra, that A1 equals x2 minus x1, A2 equals y2 minus y1, and A3 equals z2 minus z1. Okay, so what that gives me is I can actually represent A, vector A, as being x2 minus x1, y2 minus y1, z2 minus z1. And the reason that works is because vector AB is in fact a representation of OP, where an OP and A are actually the same vectors. All right, now let's go ahead and consider a simple example in R2. Now, suppose I have, well, let's first set up some axes I can work with here. Obviously, X and Y axes. Suppose I have the vector A equals 3, 2. So A is a position vector of, say, point P, which has coordinates 3, 2. So I do 1, 2, 3 on the x-axis, 1, 2 on the y-axis. So right there, this is vector A. Now, the length of A, simply by the Pythagorean theorem, take this distance and this distance. So the length of A is going to be the square root of 3 squared plus 2 squared, which is square root of 13. And also, if I think of this angle here with the x-axis as being theta, I know that tangent of theta is, well, just from basic trig, I know it's y over x. So in this case, it's going to be 2 over 3. So if I actually need to know what the angle is, I could take theta as being arctan of 2 over 3 and actually get the angle. So now let's suppose that I want to take this vector A, and I want to move the initial point to the point A is, let's say 2, 2. I'm not going to move it too far. So I want to take this point, and I really want to move it to the point 2, 2, which is like right there. I want this to be my initial point of the vector. So the end point must then be, well, I know I need x1 plus a1 equals x2. So see, a1 is 3, x1 is 2, so 2 plus 3 has to be equal to x2, which is 5. Therefore, x2 equals 5. And also I need to take a look at y2. I know that y1 plus a2 equals y2. And that's simply going to be 2 plus 2, which is 4. Therefore, y2 is equal to 4. So my end coordinates will have coordinates 5, 4. So see, 3, 4, 5. That was 2, so that's 3, 4. So 5, 4 is right here. So that would be my new vector. Now what I want to do is I want to convince myself of a couple things. Number one, for these vectors to be equivalent, then the magnitude must be the same and the angles or the directions must be the same. Well, if I drop perpendiculars here, this is going to have height 2. This is going to have length 3. So the magnitude of this new vector, I'm going to call this vector B. So the magnitude of vector B is simply going to be the square root of 3 squared plus 2 squared, which is the exact same thing of vector A. That should be a vector, which is root 13. So I know that these have the same length, even though not the way I drew it, because I'm not really good at scale. But what's the angle? Well, again, this is the distance between these is 2, and here is 3. So if I think of this angle here as phi, then tangent of phi is going to equal 2 over 3, which is the exact same thing we said up here. So obviously phi is going to be inverse tangent of 2 over 3's. So what we end up with is both the magnitude and the direction as being the same. Now here, just so you don't think I didn't cheat, I just put 2 and 3 in there. I can take a look at this as being the magnitude of B as being the square root of, well, my x's, my distance between 5 and 2, so that's 5 minus 2, that's x1 minus, or x2 minus x1 squared, plus the difference in y's, which is 4 minus 2 squared, and that is in fact a square root of 3 squared plus 2 squared, as I did up here, which obviously root 13. So what I have there is a situation where I move this vector, and the magnitude and the directions stay the same, so these are actually equivalent vectors. So let's move to R3. So given 2 points, well, actually, let's go ahead and draw a coordinate system here. I'm not going to draw this in 3 space, even though I'm going to actually be working in 3 space, which may seem kind of odd, but just for illustration purposes, I think it'll be fine. You get the idea. Okay, so given 2 points, A and B, A has coordinate x1, y1, z1, B has coordinate x2, y2, z2. The vector A with representation AB is then, just like we did, if I simply subtract these components, x2 minus x1, y2 minus y1, x2 minus, z2 minus z1. Vector A would then have representation of AB. And again, I do this in R2 because it's easier to visualize in R2. So if this is my original vector, let's say here's point A, and I'm going to go over up to point B. So this is my vector AB. And this has coordinates, where am I? 1, 2, 3, 4. So this is x is 4. Y is what? 1, 2, 3, 4, 5. That means this has coordinates 6 and 7. So if I simply take x2 minus x1, that's going to be 6 minus 4, which is 2. That is what I'm thinking of as A1 for my vector A. And then if I take y2 minus y1, I'll have 7 minus 5, which is also 2. And this is what I'm thinking of as A2. So vector A is going to be equal to 2, 2, which is right here. So this is vector A. So vector A is a position vector for the point 2, 2, which has representation AB, which goes from 4, 5 to 6, 7. So these two vectors are in fact equivalent.